Okay, this video has to do with a redox titration. And if you look at this question, basically what the student is trying to do is they're using potassium permanganate that has a certain known molarity, and they're trying to figure out how many grams of this sodium chlorate are in a certain mixture. And so the first thing that it's asking, like, what type of reaction is it? And it's obvious it's a redox titration, but the way that you can tell if something's a redox titration is if the oxidation numbers change. And anyway, you could look and you'll see that it does, but I want you to practice writing the half reactions. And so that can also help you balance the equation. Anyway, the first thing you got to do is assign oxidation numbers. So oxygen is -2, potassium is +1, and 4 times -2 is -8. So this manganese must be +7. Here sodium's +1, oxygen's -2, that's -6. So this must be +5 because +5 and +1 is +6. Cancels out that -6. This is +1, -1. This is -1, so that's 2 times -1 is -2. That means that that's +2. This is -2 +1. This is -2 +1. So that's -8. That makes that +7. This is -1. This is +1. And so you can see that the manganese goes from +7 to +2. So when the oxidation numbers change, that means it's an oxidation reduction reaction. If they don't change, then it's not. But anyway, write the half reaction. So we start off with this manganese, it's +7. And anyway, we're going to add electrons to it because it's going to have to go down to +2. So we know that it's got to change into manganese +2. And so you always add the electrons to the side that has the most positive charge. So add 5 electrons because 5 and 7 gives you a net of +2. 5 negatives, 7 positives. All right. Manganese's oxidation number goes down. You could say it's being reduced. Okay, now the other thing that changes is the chlorine. And here it's +5. And I know the electrons are going to have to go on the other side because if one thing's reduced, something else has to be oxidized. And then it goes to chlorine +7. Its oxidation number goes up, so it anyway has to lose 2 electrons. And so if the oxidation number goes up, that's a good sign that it's being oxidized. Now, we can use these half reactions to help us balance the equations because the electrons lost, okay, must be equal to the electrons gained. Well, 5 doesn't equal 2, so you got to find a common number that they both go into. And 5 and 2 both go into 10. So we'd multiply this by 5 and this by 2. Now that helps us balance the equation by knowing that there's a 2 there and a 5 there. Okay, then the rest of it I'll just balance. This is 6, this is 2, this is 3, this over here is 5, and this one over here is 2. Now, on the AP test, normally they give you this equation like this already balanced. It would look something like this right here. They would give you that usually. But anyway, all right, this says calculate the mass of sodium chlorate. So we're trying to get the grams of this. Okay, using the volume and the molarity, and they want us to use it from trial 2. So in trial 2, this is 0.01 molar, and this is 12.25 milliliters. So what they're saying is when you add 12.25 milliliters of this, it reacts with all the grams of this sodium chlorate. All right, anyway, so they want us to calculate that. So what we'll do is we'll start off with the volume of the potassium permanganate, KMnO4. Now, and I forgot to write milliliters. Okay, so whenever you have a volume and you know its molarity, if you put the molarity in the right way, KMnO4, I'm breaking it down into its components. For 1,000 milliliters KMnO4, that automatically gets you into moles. All right. So then after moles, doing stoichiometry comes the mole ratio. And so the mole ratio is 2 moles of KMnO4 reacts with 5 moles of potassium chlorate. Then we want to change to grams because that's what it's asking for. So 1 mole of potassium chlorate, NaClO3, and the molar mass of that is, let's see here, 106.44 grams, 106.44 grams of sodium chlorate. And if you do the math, that ends up being 0.033 grams of sodium chlorate. Okay, next problem. I don't know how this thing got in there, but it doesn't need to be in there. I need to get rid of that. I'm just going to hit delete and see if that gets rid of it. All right. So anyway, calculate the percent of sodium chlorate in the mixture. And so if you go back to trial 2, the mixture is 0.632 grams. So we know that the mixture is 0.632 grams of mixture, but it wants the percent of sodium chlorate, so it's always the part over the whole, 0.33 grams sodium chlorate. We'll multiply that times 100, and we end up getting 5.22%, or 5.2% of sodium chlorate. All right, now give one possible reason or error in the experimental method as to why the volume of KMnO4 in trial 1 is significantly higher than in trial 2 and 3. Well, one common mistake that people make when they do a titration using a burette tube is they rinse the burette tube out with water or whatever, and so they rinse it all out with water, but then when they add the potassium permanganate, like let's say that's the red stuff, they add it, there's some water that's left in the tip. And so when you start adding this into a beaker, basically you're adding some water before you add any of the potassium permanganate. So maybe the student forgot to do it. So what you want to do first with the burette, this is like a lab procedure, you should know. First, you rinse with water. Rinse with water. But then you want to rinse your burette tube with whatever you're using to titrate with. And so in this case, it would be KMnO4. You want to fill it with KMnO4, and you want to rinse it. Well, anyway, you get the idea here. You want to rinse it twice with whatever you're titrating with. All right, that's a lab procedure you should know. Okay, next. This is photoelectron spectroscopy. And so they're giving you this here, and this is the PES scan, and they want you to figure out what it is. Now, one thing, this got kind of cut off, but this down here is the binding energy. Now, I want to show you something that's important. Depending upon where you get these graphs from, sometimes they label it from the least amount of energy to the greatest, and sometimes they're labeled backwards from the greatest to the least, and I believe AP does it the other way around. AP would have the 1000 over here, but it just depends upon where you get the graphs from. Now, this is more energy, this is less energy. Okay, this is the amount of energy it takes to hold the electrons to the nucleus. And basically the energy is given from the charge, the positive charge, that's the nucleus, times the charge of an electron divided by the distance the electron is from the nucleus. So basically the closer to the nucleus, the more energy that it takes to remove it, okay, or that it's held with. So over here, if you look at this graph, the nucleus, okay, would be over here. There's the nucleus, and it's holding these electrons. These peaks represent electrons. So we can just write an electron configuration. 1s2, 2s2, 2p6. Notice that that's 3 times as high because 2, 4, 6 electrons. 3s2, 3p6, and then it goes to 4s, and that's 1 because it's half of whatever 2 is. If you can see that. All right. Now circle the top of the peak that represents the 2p orbital. So that's going to be right there. Okay, on the graph, draw a 3s peak for magnesium. Okay, so sometimes the way to figure this out is this one. Oh, we forgot to identify the element. It's 4s1, so that's potassium. Okay, so this is potassium. So what I like to look at is, okay, potassium has 19 protons. And so I draw these half shell models. And so in the first shell, okay, you have 1, 2, 3 shells of electrons, and then potassium has actually 4 shells. Okay, and so there's an electron right there in the fourth shell. Now, magnesium only has 12 protons, and it has the first shell. There's 1, 2. I forgot to label these. Okay, the second shell. Okay, and the third shell. Okay, now they want us to draw the 3s peak for magnesium. And magnesium's electron configuration is 1s2, 2s2, 2p6, 3s2. Okay, that's magnesium. So it has 2 electrons in it. Now, however, magnesium only has 12 protons holding on to these electrons, or pulling in on them, or holding on to them. So basically, if we're looking at the third shell for potassium versus the third shell for magnesium, potassium has more electrons holding it. So potassium is going to have, in its 3s, it's going to take more energy to remove an electron from potassium's 3s than it would magnesium, because magnesium has fewer protons. Okay, so magnesium's 3s is going to be somewhere probably over in here somewhere, because it's going to take less energy because it has fewer protons binding the electrons. Okay? The potassium has more protons binding the electrons, so it's going to take more energy. Magnesium has less. So this would be magnesium's right there where I drew it. Okay, that's it for this video.